Let's take a look at a specific type of free response problem, ones that we often see that involve rates and accumulation. And I think we want to get our students to try and see some things early on in the process. So on this slide, I have just the question itself, without any of the parts that ask students to do certain things. Kind of sets the scene, and I wanted to highlight a couple things that I thought we want to show students they want to be able to pick up on when they read a question. So first and foremost, on a typical day, the snow on a mountain melts at a rate. Let's just kind of highlight that right there, right? At a rate modeled by this function, right? Now here's what I like to point out to students is that they're not showing you that typical F prime symbol, right? That's okay though. They've mentioned the fact that this is a rate, so this is a derivative, and I think that that's really important for students to pick up on right to begin with. So it's melting, which means that the snow is going away. Meanwhile, a snowmaker adds snow at a rate modeled by this particular function. So we also want to pick up on the fact that both M and S have inches per hour as their units, right? And we want to make sure we understand the time involved, 0 to 6 here. And then lastly, we want students to pick up on the idea that there are 40 inches of snow to begin with. So we want them to start thinking about, even before they start looking at parts A, B, etc., what might they ask me? What might I be asked to do? So you look at these rates. If you're giving me rates, you might ask me to find how much snow has melted or how much snow has been added, things of that nature. You might ask me when the snow on this mountain is at its highest or lowest. And these are the things we want students to think about critically before we even enter the problem-solving phase. So trying to get your students used to seeing these kinds of things. Okay, let's look at the parts specifically. Now, in part A, it says how much snow will melt during this 6-hour period. So what I always, and indicate units of measure is a really big thing, because I want students to understand that when you see this kind of thing, when you're being told indicate units of measure, there's a really good chance that you will get a point for units, right? So we want to make sure they understand units point is possibility here. Now, going back to the problem itself, I say, let's think and brainstorm first before we just get right to pencil to paper. So how much snow? How much snow? That's inches, right? So in order to go to inches, I have to take my rate, which is my melting, right? And I have to integrate that. So I want students to be thinking about, I'm going to have to integrate that function they gave me, m of t, from 0 to 6, right? And it actually turns out that if you do that, you get 2 inches. So we want to make sure we abide by their idea of indicating units of measure. Now, let's go to part B. Write an expression, they're calling it I of t, for the total number of inches of snow. So if I'm going to get total inches of snow, I need to know not only how much snow melted, but how much snow was added, and I have to remember that we started with 40 inches of snow to begin with, right? So we have the 40 inches of snow, right? So I of t, let's call this, is going to equal that 40 inches of snow plus the total amount of snow added, right? So that was that function that they had given s of t, right? And then minus the total amount of snow that has melted. And so actually I'm going to change these upper limits of integration to t because it just says at any time t. So here I have a nice little expression that is helpful in finding how much snow there is on this mountain at any particular time. Now, if I had to note where students might make a mistake, I would say it's right here at this 40, because students will think about the melting and the adding, but they might not remember earlier on in the problem we were told about that initial value. So very important there. And of course, you can tell your students that this is very much like any other problem they would do. If we were talking about velocity and position and things of that nature, they'd want to know, well, where did I start originally? Where did the particle start? Okay, so let's go to part C now, right? Find the rate of change of the total amount of snow when t equals 3. So that means I need to derive I of t. So we want to derive each piece, if you think about it, right? So 40 becomes 0, right? The derivative of 40 is 0. The derivative of an integral is our second fundamental theorem, so plus s of t, right? And then same thing here, minus m of t. And of course, we'll be evaluating that at t equals 3. And so you should get a value of 0.19376. And of course, they didn't ask for it here, but we're going to give it to them anyway. Inches per hour. Always important, right? Now, interesting little extension here that we can talk about, something that maybe piqued the students' interest. Take opportunities as you're reviewing to try and get the students to think about other things. Let's not be locked into the problem in front of us, right? Let's think about what else we could do with this kind of problem. So what we could be asked is interpret, right? Interpret this value right there. What does that mean? And so if we have a positive rate of change of snow, that means more snow is being added than is melting at the time t equals 3. And that might not be true of all the times, but it is at that moment in time. So we want students to be thinking about other things than just what they're reading, right? And then finally in part D, it says, when's the snow maximum? So we want students to get that you've given me a closed interval, and this makes a direct connection to the extreme value theorem, right? And this is way back in the beginning of the year now. So do they remember that we have to make sure we see how much snow there was at time 0, how much snow there was at time 6, and then how much snow there was at any, and I'll put it in here, critical value, right? And it just so happens that there is a critical value when I prime is equal to 0, and that occurs at t equals 4.24055. And so you may have students who realize that this is exactly when the amount of the rate at which the snow is melting is equal to the rate at which it's being added. And so once we test all of these out, what turns out happening here, and you can kind of do it on your own, is that we started with 40 inches of snow at 0. At 6, we get up to 41.492, and this is me just using part B here. And then at the critical value, it actually winds up that that's where we have our maximum of 41.651 inches. And so we have to look for these opportunities to extend the concept, and if you can do that for your students, I think that that's going to be super helpful. So the next video, we'll look at a different type of free response problem, look at where some points can be had and different little things that students want to pick up on while they're fleshing out a free response question. I hope this has been helpful, and you feel free to look for ways in your experience and in other free response problems where you could take a problem and go with it. Make a part E or a part F out of it. Really get the students to connect a lot of things that they've been learning throughout the entire year.